Hello, everyone. Today we're going to be going over the code for homework 4. So this is the Transpiration and Stomata lab. Before we go over that code, though, I want to go over t-tests. So remember that for a t-test, our null hypothesis is that sample 1 and sample 2 are drawn from the same distribution, so they represent the same population. And then our alternate hypothesis is that sample 1 and sample 2 are drawn from different distributions, so they would represent different populations. So in our hummingbird example that we saw on the first week of class, the p-value for this test was 0.591, which is less than our alpha value of 0.05, so this result is not considered significant. So one new piece of code that we're going to be seeing this week is the grid arrange function. This is in a new package, the grid extra package, and this is what allows us to combine multiple plots into one image. So we will need to install a new package this week called grid extra. Make sure that that E is capitalized. And then to use this grid arrange function, we're going to give the new plot a name. And then we're going to use our arrow to point at that name and call it the grid arrange function. And then in parentheses, we're going to have the grobs, which is short for grab objects. And then we're going to have that equal to a list where we name the plots that we want to grab. So plot 1 and plot 2. And then we're going to do a comma, and we're going to say the n row, the number of rows, is equal to some number. And then a comma with top equals some title that we want to give that graph. So an example for our homework, if we want to name this new combined graphs to model density, then we can call up the grid arrange function and grab the objects of the upper stomodal density graph and the lower stomodal density graph, and we want those to be in one row, and we want the title of that graph to be stomodal density. All right, so let's go ahead and open up the R code and get started on the homework for this week. So as with all R codes, the very first thing we're going to do is clear our workspace. And then the next thing we have to do is set our working directory. So you guys can go into a previous code from a previous week and grab that line and paste it here, or you can do it manually by going to Session, Set Working Directory, and Choose Directory. And then we can choose the folder that we want. And then I'm going to copy this line of code where I set my working directory. And I'm going to paste it up here so that when I run this code later, I don't have to set that working directory again. All right, so I ran that line of code, and the next thing we have to do is install a new package. So this is the grid extra package. So I'm going to go ahead and install that package. And then after we install it, we're going to load all of our packages. So we're going to use the same 3 packages that we've been using, plus this new grid extra package. So I'm going to run those 4 lines. And if you see this error, object is masked, that's fine. Just ignore that. It's not important for us. And the next step is to read in our data set. So we're going to name our data, and then we're going to call up the read.csv function. And then we can type the name of our data file, which is going to be homework4_data. And I'm using the example data set, but if you're working on the homework, you're going to want to use the homework data set. All right, so I'm going to run that line of code, and you can see now that we have our data over here in the environment. And now I want to view the names of all of the variables in our data set. So I'm going to call up the call names function and see the column names for our data set named data. And you can see now that we have a column called plant, a column called transpiration rate, upper density of stomata, and the lower density of stomata. So our first task is to find the summary statistics for transpiration rate, and we want to group this by plant type. So we're going to name this table transpiration.rate, and then we're going to call up our data set named data, and we're going to pipe that to the group by function, where we're going to group by plant. And then we're going to pipe that to the summarize function, where we can find all of our statistics. So first we have the mean, and we want our mean to be equal to the mean of transpiration rate. So I'm going to go down here to where we name that column And I'm going to copy this variable and I'm going to paste it right here. So now we're finding the mean of transpiration rate. And I'm going to do the same thing for standard deviation, paste that value right there. And the same thing again for our minimum and our maximum. So now we have all of our summary statistics for transpiration rate. So I'm going to go ahead and run that line of code. And now you can see we have a value in our environment called transpiration.rate, where we have all of our statistics. And then to view that table, we can just call the name, which is transpiration.rate. And all of our summary statistics are going to appear down here in the environment. So you can copy those into your homework assignment. All right, so now let's view the names of our columns again. So nothing's changed here. We have the same column names. And our next task is to create a summary statistics table for stomatal density on the upper and lower leaf surface, again, grouping by plant type. So we're going to name this table stomatal.density. We're going to call up our data set named data. We're going to pipe that to the group by function where we group by plant. And then we're going to pipe that to the summarize function where we can find all of our summary statistics. So you'll notice that in our table up here, we're naming mean, standard deviation, SD, and so on. Whereas in this table down here, we're naming our mean upper density, and then down here we have mean lower density. So we can combine multiple summary statistics into one table and just give them different names so we know what they all are. So the first four are for the upper stomatal density. So we have the mean, standard deviation, minimum, and maximum of upper density. So here we're going to want to copy the variable for upper density dot stomata dot meters squared. So I'm going to copy that variable name and paste it right here. And then I'm going to do the same thing for standard deviation, the same thing for our minimum, and the same thing for our maximum. So now we have the mean, standard deviation, minimum, and maximum of upper density. And then we can do the same thing for our lower density. So I'm going to copy the variable name right here. Copy that. And now we can paste it into these summary statistics. So we have the mean of lower density, which is equal to the mean of the lower density of stomata. And then I will paste this variable name for standard deviation, for the minimum, and the maximum as well. So now we have all of our summary statistics for the upper density and the lower density, and those are all going to be combined into one table that we named stomatal density. So I'm going to run that line of code, and now you can see that that table has popped up in our environment. We have stomatal.density. And then to view that table, we can just call the name of the table, which is stomatal density. So I'll run that line of code, and you can see that we have all of our summary statistics here. We're grouped by plant type, so we have the Chinese evergreen and then the hibiscus. And we have our mean of the upper density, standard deviation, minimum and maximum of upper density. And then our mean lower density, standard deviation. And you can see that it has two more variables that were cut off. But if we make this a bit bigger and rerun that, we can hopefully see that. There we go. So now all of those values are popping up. If you're not able to make this large enough, you can always just click on the table over here, which will pull up the whole table, and you can copy the values from there. All right, so now that we have all of our summary statistics for the upper and lower stomatal density and transpiration rate, our next task is to graph stomatal density. So let's view our column names once again. Again, nothing's changed here. We still have the same column names. Make this a bit bigger. So the first graph that we're going to make is the stomatal density on the upper leaf surface. And we have a hint that X is a grouping variable. So we're going to name this graph upper.stomatal.density. And then we're going to call up the ggplot function. And we're going to set our data equal to our data set that we named data. And then we have to set our aesthetics with an X and Y variable. So we have X as a grouping variable, And we know that the grouping variable we have is called plant. So we can fill in plant for our X value. And then for Y, we want the upper stomatal density. So I'm going to go down to where we called up our column names, and I'm going to highlight the upper dot density dot stomata dot meters squared. I'm going to copy that and paste that as our Y value here. So now we have an aesthetics with our X equal to plant and our Y equal to the upper density of stomata. And then we're going to call up the geom box plot function to make box plots. And here we have outliers equals F, which stands for false. So we're not going to plot outliers on these graphs. It makes the graphs much easier to read and interpret. And then the last thing we're doing is adding some labels. So we don't need to add a label for our X variable because those are going to already have labels for the plant type, but we do need to have a label for our Y value and a title. So for our Y variable, we're graphing upper density of stomata. So we can just say stomatal density, and we need to include units. So this is stomata per meters squared. And then for your title, go ahead and name it something like upper leaf surface. So now we have a label for our y-axis and we have a title. So let's go ahead and run the line of code where we make our graph. And then to view the graph, we're just going to call the name of that graph. And this is what our box plot looks like. So you can see that the median value for upper stomatal density in the Chinese evergreen is 0. And the median value in the hibiscus is a little bit higher, but for the most part, there's not a lot of stomata on the upper leaf surface in either of these plants. All right, so now let's graph the stomatal density on the lower leaf surface. So this is going to look pretty much the same as above. We're naming this graph lower.stomatal.density. We're calling up our ggplot function, and we're setting our data equal to our data set that we named data. And then we're going to set our aesthetics with our X value, again, equal to plant. And then our Y value here, instead of upper density of stomata, we're going to want the lower density of stomata. So I'm going to highlight this variable name here. I'm going to copy that. And then I'm going to paste it as my Y value. So I have Y is equal to the lower density of stomata. And then again, we're calling up the geom box plot to create box plots. We're not plotting outliers, but we do need to add labels for our graph. So we can use the same labels for our y-axis, which is just stomatal density. Save myself some typing. I'm going to just copy what I wrote up here. And I'm going to paste it for my y-axis label down here. And then the title, instead of upper leaf surface, we can name this lower leaf surface. And now the graph is done. So we have an X and a Y axes. We're using box plots without outliers. And then we have labels for our Y axes and our title. So let's go ahead and run that line of code to create the graph. And then we will call the name of the graph to view it. So this is what the stomatal density for the lower leaf surface looks like. You can see that the Chinese evergreen has a much higher stomatal density on the lower leaf surface than the hibiscus. There's also much more variation in stomatal density. So our next task is to combine both of these graphs into just one image. So here we're naming this combined graph stomatal.density. And then we're calling up the grid.arrange function, where we're going to grab the objects, which are in list form, and the objects are upper.stomatal.density, which is the name of our graph up here. And the second one is lower.stomatal.density, which is our graph that we made second. And then we want the number of rows equal to 1, so we want those graphs to be side by side. And then the top, we need a title here. So I'll let you insert your own title. Make sure it's an informative title. Please don't use week 4 graph. Tell me what's being actually graphed there. And once we run this line of code, then we will create the object where both of these graphs are combined into one image. And it pulled up the graph right away. So here is our graph. We have an informative title on the top. And then we have our two graphs side by side for upper leaf surface and lower leaf surface. Both of them have the axes of stomatal density, and they're both grouped by plant type. So you can see both of those graphs side by side next to each other. All right, and then we have to save this graph so we can attach it in our homework. And you can name this JPEG anything you want. I'm going to say week.4.graph. And that's going to be the name of the JPEG. And then the comma here, this is the name that we're actually saving. So stomatal.density is the name of the graph where both the upper and lower are combined. And then we want the width to be 12 and the height to be 6. So after I run that line of code, then in the folder that I set my working directory as, the JPEG will appear with the image of both of these graphs. All right, so now we're ready to run some t-tests. But remember, to run a t-test, we have to create some subsets and we have to organize our data so that all of our numeric variables are in one column and all of our grouping variables are in another column, and all of the data in that data set will be used for the t-test. So the first thing we want to do is create a subset with only the Chinese evergreen, so we can test the stomatal density of the upper and lower leaves in Chinese evergreen. So we're going to name this subset Chinese.evergreen. We're going to call up our data set named data, and then we're going to pipe that to the subset function, where we want to subset the plant equal to, and we want this to be Chinese evergreen. So it's Chinese.evergreen. And then we're piping that to the select function. So we're only selecting specific columns of our data, and we just want the column called lower density and the column called upper density. So I'm going to run that line of code. Let me move this out of the way. And now you can see that we have a new data set in our environment called Chinese.evergreen. We have two variables, so two columns with 36 observations. The next line of code, we're reformatting the data so that all the stomatal densities are in the same column. So if we click on it before we run this line of code, we have one column for lower density and another column for upper density, but we want all of these numbers to be in one column, and then we want the other column to tell us if it's upper or lower. So we're going to use the pivot longer function. So we're going to rename our data set Chinese.evergreen. We're calling up the subset Chinese.evergreen, and then we're piping that to the pivot longer function, where we're selecting the columns 1 through 2, which is all the columns. And then we want our names, so the name of the columns now, to go to a new column that we call leaf.surface. And then we want all the numbers in those cells to go to a new column that we call stomatal.density. So we have names going to a column called leaf surface and values going to a column called stomatal.density. So if we run this line of code, looks like nothing happened, but something did happen. So if we click on this Chinese.evergreen subset, now you can see we have a column named leaf surface where we list lower or upper, and we have a column called stomatal density that has all of our numbers. So this is a reformatted version of our subset. So now we're ready to run a t-test. Let's view the column names one more time. So we have a column called leaf.surface and a column called stomatal.density. So this t-test is comparing stomatal density on the upper and lower leaf surface, and we're using the Chinese evergreen. So we're going to use the t.test function, and we're going to list our numeric variable first, and then this little tilde sign means as a function of, and then we're going to name our grouping variable. So our numeric variable, the column that has all the numbers in it, is the column that we call stomatal.density. So I'm going to copy this column name And I'm going to paste it right here. And then our grouping variable is called leaf surface. So I'm going to copy this column name and I'm going to paste it right there. So now we're running a t-test comparing stomatal density as a function of leaf surface with our data equal to only the Chinese evergreen. So I'm going to run that line of code. And you can see that we have quite a significant p-value here that's really small, 9 zeros in front of that 3. So we can say that there is a significant difference in the stomatal density between the upper and lower leaf surfaces in the Chinese evergreen. All right, so now we're going to do the same thing we did with the Chinese evergreen, but with the hibiscus plant. So we're creating a subset that we name hibiscus. We're calling up our main data set that we name data. And we're piping that to the subset function where we want our plant equal to, and this is going to be hibiscus. And then we're piping that to the select function where we select just the lower density and the upper density of stomata, and we're getting rid of all of the other columns. So I'm going to run that line of code, and now you can see we have a new data set in our environment called hibiscus. We have 2 variables, so 2 columns of data with 29 observations. And then again, we have to use the pivot longer to create 2 new columns with all of our numbers in one column and all of our groupings in another column. So again, we're just going to rename this data set hibiscus. We're piping that to the pivot longer function where we select the columns 1 through 2. And then we're moving the names, the column names, to a new column that we call leaf surface. And we're moving the values, all the numbers, to a new column called stomatal density. So same thing as above. So if I run that line of code, now you can see over here that our hibiscus data set now has 58 observations, but still 2 variables. All right, so we can view the column names of this subset. Again, the columns are leaf.surface and stomatal.density. So now we're ready to run our t-test. Again, comparing the stomatal density on the upper and lower leaf surface in the hibiscus plant. So we use the t.test function, and we want to name our numeric variable first, which is going to be stomatal.density. So I'm going to copy this and paste it as my numeric variable. And that's as a function of our grouping variable, which is leaf surface. So I'm going to copy this column name and paste it right here as our grouping variable. And then we have our data equal to our subset named hibiscus. So if I run this line of code, now we have a t-test and our p-value is 0.02. So a lot larger than our p-value in the Chinese evergreen, but still less than that alpha value of 0.05. So this is still significant. There is a significant difference in the stomatal density between the upper and lower leaf surface in the hibiscus plant. All right, so now we're moving away from these subsets that we created and moving back into our main data set. So let's refresh ourselves on what the column names are for our main data set. Again, we have a column named plant, a column named transpiration rate, upper density, and lower density. So now we want to compare the stomatal density of the upper leaf surface between the Chinese evergreen and the hibiscus plant. So the 2 upper leaf surfaces. So for our t-test, remember we want to list our numeric variable first. So our numeric variable for upper leaf surface here is going to be this upper.density.stomata.meters squared. So this is where all of our numbers are. So I'm going to copy that column name and paste it right here as my numeric variable. And that is going to be as a function of our grouping variable, which here is called plant. I'm going to just type out the word plant. That one's pretty easy. All right, so now we have upper density of stomata as a function of plant, and we're using our main data set that we named data. So if we run this t-test, you can see that our p-value now is 0.5498. So I will let you guys interpret that value. Tell me if that's significant or not. Is there a difference in the density of stomata on the upper leaf surfaces between these two plants. All right, and again, we can view our column names. And now we're ready to run a t-test comparing the stomatal density of the lower leaf surface between our two plants. So same thing as above, except instead of upper density, now we want lower density. So I'm going to copy this column name for lower density of stomata. And I'm going to paste it right here as my numeric variable. And then again, our grouping variable is plant. So I'm going to just type plant. You can copy and paste if you want. So now we have a t-test comparing lower density of stomata as a function of plant type with our data set, our main data set named data. So if we run this t-test, you can see that our p-value is 0.455. Again, you guys should interpret this. Tell me if there's a significant difference in the stomatal density of the lower leaf surface between these two plants. All right, and once again, let's view the names of our columns. Nothing's changed, everything looks the same here. And now we're ready to run one more t-test comparing the transpiration rate between the Chinese evergreen and hibiscus plant. So again, our numeric variable this time is going to be transpiration rate. So I'm going to copy this column name and I'm going to paste it up here as my numeric variable. So we want to test if transpiration rate is significantly different between plant types. So again, our grouping variable here is just plant. And if we run this t-test, you can see that our p-value is 0.4018. So tell me if there's a significant difference in transpiration rate between the Chinese evergreen and the hibiscus plant. Okay, now we're ready to start part 2. So again, let's just refresh ourselves on these column names. Nothing's changed, our same 4 columns that we've been working with. And now our task is to standardize transpiration rate per stomatal density. So we're going to add our new column to our data set named data. We're calling up the data set named data so we can add to it. We're piping that to the group by function, where we're going to want to group by plant type, right? Our grouping variable for this data set is plant. And then we're going to mutate. And remember, this is how we create a new column in our data set. So we're mutating and we're creating a new variable that we name std or standard.transpiration. And we want that value to be equal to the transpiration rate per, so divided by stomatal density. So let's add in transpiration rate. I'm going to copy this column name here. And I'm going to paste it right here. So we have standardized transpiration rate is equal to the transpiration rate divided by stomatal density. So here you guys need to figure out if the upper leaf surface or the lower leaf surface is a better representation of the overall stomatal density. If you think that the upper surface is a better representation, you would divide by the upper density. But if you think that the lower density is a better representation, then you would divide by the lower stomatal density. For this example, I'm going to select the upper stomatal density, but I expect you guys to give this a bit of thought and try and decide which one of these values better represents the overall stomatal density of the plant. So here I'm creating a new column that's called standardized transpiration rate, where I divide the transpiration rate by the stomatal density. So if I run that line of code, and we can view the column names again. So if I see the column names, now you can see we have a new column in our data set called std.transpiration. So this is that standardized transpiration that we just created. All right, and now we want to create a summary statistics table for our standardized transpiration rate. So we're naming this table std.transpiration.rate. We're calling up our data set named data, and we're piping that to the group by function, where we want to group by plant. So our grouping variable for this entire data set is always going to be plant. And then we pipe that to the summarize function, where we want to find a mean that is equal to the mean of standardized transpiration rate, which our column name for that is std.transpiration. So I'm going to copy that column name here, and I'm going to paste it in here. So now we can find the mean of standardized transpiration, and I'm going to paste that here for our standard deviation, for our minimum, and our maximum. So now we're finding all of our summary statistics for our standardized transpiration rate. And if I run that line of code, somewhere over here, yeah, right here, we have a new table in our environment called std.transpiration. To view that table, we can just call the name of it. So if I run that line, here are all of our summary statistics. And this looks kind of weird because I chose upper density of stomata in which there were a lot of zeros. So that's why I have all of this. Hint as to which one you should be choosing. Okay. So if we view the column names again, so the column names of our data set, again, we have the 4 variables we've been working with: plant type, transpiration rate, and then the upper and lower stomatal density, and then that new variable we created of standardized transpiration rate. And now our job is to graph standardized transpiration rate. So we're naming this graph std.transpiration.graph. We're calling up our ggplot function where we set our data equal to our data set named data. And then we want our aesthetic set so that our x value is equal to our grouping variable, which is plant type. So I'm going to write plant there. And then we want our y value to be equal to the standardized transpiration rate. So the column name for that is right here. I'm going to copy that column name, and I'm going to paste it as my y variable. So now we have x equal to plant and y equal to our standardized transpiration rate. And then we call up our geom_boxplot function, where again, we're ignoring outliers so we can actually interpret our graph. And then we have to add some labels to our graph. So our y value is standardized transpiration rate. So I'm going to say standardized transpiration rate. And then we need units here. I'm going to let you guys figure out what the units are, but just think we had transpiration rate, which is moles per meter squared per second. And we divided that by stomatal density, which is in stomata per meter squared. So you should be able to figure out what the units are for our standardized transpiration rate. And then we need to add a title to our graph. So tell me what variables are being plotted, what groups are we looking at? Give me a nice informative title. All right, and then this graph is done. So now I can run this line of code to generate the graph, and then I can call the name of that graph to view it. So if I do that, move this here. So when you standardize transpiration rate using the upper stomatal density, this is what your graph would look like. So we have plant type on the bottom here and our standardized transpiration rate with units on our y-axis here. You can see that the Chinese evergreen has a much lower standardized transpiration rate when we look at the upper stomatal density. Yeah, so then we're ready to save the graph. Again, we just have to give this JPEG a name. I think I already named my graph earlier, week 4 graph, so got to do something else here. I can say week.4.std graph for standardized transpiration rate. And then we're going to call the name of the graph that we want to save, and we want the width equal to 6 and the height also to be equal to 6. If I run this line of code, yeah, so this warning message saying removed 30 rows, Again, this is a problem because there's so many zeros in the upper stomatal density. So it's telling me that there's a bunch of zeros there that it wasn't able to graph, which is fine. Again, hint onto which leaf surface you should actually be choosing. Okay, and then if we look at our column names one more time, again, same 4 columns we've been working with: plant type, transpiration rate, stomatal density of the upper and lower surface, and then our standardized transpiration rate, which is the variable we created earlier. And our very last task is to run one more t-test comparing the standardized transpiration rate between the 2 plant types. So remember, for a t-test, we name our numeric variable first and our grouping variable second. So our numeric variable here, we're comparing the standardized transpiration rate. So we want to use this std.transpiration. So I'm going to copy that column name and paste it right here. And then our grouping variable is plant. So I'm going to just write plant. And if I run this t-test, okay, so this t-test didn't even work because there's too many zeros. Let's just fix that really quick. So instead of doing the upper, let's do the lower. And rerun all of this. All right, and now our t-test is working. So when we use the lower stomatal density, our p-value is 0.84. So tell me if that is significant or not. Is there a significant difference in the standardized transpiration rate between the Chinese evergreen and hibiscus plant? And you can see that when we standardize with the lower stomatal density, these box plots do look a little bit different. Yeah, I think that is all for this week. Be sure that you save your R code as a .r file and attach that in Canvas along with your homework. And again, you should be submitting 2 assignments or 2 files, either a Word document or PDF, which has all of your tables and graphs and answers all the questions. And then the second document should be this R code as a .r file. And this helps us grade and figure out where you went wrong, if you deserve any partial credit for errors. If you don't attach your R code, we won't be able to do that for you. So please attach your R code. And again, if you guys have any questions, feel free to reach out. We're always around to help. And we will see you guys next week.